Swayam Prabha. Digital India. Educated India.
Hi, welcome back. So, I think what I'm going to do in the next few classes is to take up specific, examples and walk you through those. In a class like this, it's difficult to sort of have, numerical examples that you would have probably in an undergrad class or a class of that nature, really. So here there is a lot of conceptual understanding and writing codes, as it were, and that doesn't, I can't sort of do an example of that. I try to do as best possible, like, trying to show how you set up a CFD solution. I just basically set it up. Okay. So let's do this. And hopefully, slowly with that we'll get more ideas of how we implement all of the ideas that we were discussing so far and talking about them, right? Okay, so say I have an example which is like this. Okay, so this example says, show that mean velocity in a pipe with fully developed turbulent flow is of the maximum velocity. Okay, assume 1/7 law. I don't think we've spoken about this law earlier, right? So let's do that now. Okay. Okay, now Prandtl found, right, for turbulent flow for RE less than 10 to the power 7, right? So according to Prandtl, for turbulent flow, right, right, the velocity in the boundary layer, right, velocity, free stream, right, and this is the essentially the 1/7 law, right. So essentially Prandtl is giving us a relationship between the velocity in a turbulent boundary layer in terms of the free stream velocity, the distance from the wall, and the boundary layer thickness, right. So that's what this is about, right. Now, if I take a gradient of this, right, if I take a gradient, this is equal to u infinity 1/7 delta to the power -1/7, and y is equal to -6/7, right. If I took a gradient of this, so this is the gradient of velocity at the this is the gradient of velocity, right. Now, if I take this at the wall, right, is 0. Okay. Therefore, right. So, this is if at the wall, if we take this gradient the way we have written it here, right, according to the 1/7 law, right, then at the wall for where y is 0, right, du dy tends to, it seems to become infinite, right, and this cannot be true, right, this cannot be true. So, this has to be wrong. So, this has to be incorrect, right. So, the way he explains this, right, he basically then says that in that case basically this law that you have is not valid for a certain range of for a certain height of fluid which is right next to the wall, and that would be a laminar flow, right. That would be laminar flow, and therefore, this law which is for essentially a turbulent flow is not valid there, right. Right. So, if I was to how to explain that, so incorrect. So, how do you explain that? So, let me actually first draw that. So, essentially what we are saying is that you have this, right, and at some location right, you do have a boundary layer profile, right. So, this is all this is the velocity, right. So, here, right, this here is the free stream, right, and this is your boundary layer, and this expression that we drew up, right, the 1/7 law, however, does not seem to be valid right next to the wall. So, we are tempted to think that, I am exaggerating this, that there is a certain height here, right. So, this of course is the velocity, right. So, we were trying to figure out what kind of velocity profile would this be when this is a turbulent boundary layer, right. So, we said that this is equal to this, but we find that near the wall, however, this does not seem to hold. So, we do think that this one, this is actually this bit, okay. This is actually a laminar sublayer, okay. So, we need to sort of, so this value is actually not going to be, so this relationship is the 1/7 law is not going to be valid in that laminar sublayer, okay. We will find some distances though. Now, so essentially if I were to write that down, so explanation, so I explained it, so existence of laminar sublayer right next to the wall, right. Now, in this layer the velocity, so basically what we think is that in this layer, in this laminar sublayer, the velocity grows quickly, right. Here velocity will be 0 and then it grows quickly and then it merges with the turbulent part, right. So, in this layer, so essentially the slope is quite sharp, high, I guess, right. So, in this layer the velocity grows quickly and merges with the turbulent layer, right. Now, the gradient, however, is the same, right, for both the interface of laminar and turbulent flow, right. So, at the gradient is the same, right, you have the same gradient at the interface. So, same gradient at the interface. Okay. Therefore, of course, the drag, right, on the surface is due to the wall shear stress, right, in the laminar sublayer. Okay, this is important. Therefore, drag is due to the wall shear stress in the laminar sublayer, right. Okay. All right. So, in that with that, okay, now let us look at what we were the problem is, right. So, what is being asked of us. So, show that the mean velocity in a pipe with fully developed turbulent flow is a certain fraction of the maximum velocity, which is the free stream, right, assuming 1/7 law. So, essentially what we know is that the velocity in the turbulent in the turbulent boundary layer is given by Prandtl for Reynolds number less than 10 to the power 7 by the 1/7 law, which is this, right. Okay. So, in that case, all right, now let us then so this is a pipe cross section. Okay. Okay, fine. Okay, all right. This now then let us let us take a ring, right. Now, why are we doing this? We are doing this because in a pipe the boundary layer will, this is the right. So, essentially here, so the boundary layer is going to extend to the walls, right. So, this, so let us just say okay. Now, this, right. So, if I were to look at the side view of this, something like that. Okay. So, in here how does the boundary layer, how will the boundary layer look like? It is going to extend to the, so let us draw that. Okay. All right. So now, so essentially the boundary layer is going to extend to both heights, right. So which is what we are seeing here, right. So this is the top view of the pipe, right, and this is the side view. Okay. Now then, so the velocity, so probably it's going to look something like this, right. Probably it's going to look something like this. So if I were to draw both sides, it would probably look something like this. Yeah, is that right? Okay, right. So now let me just define a few things. So in here, so we're going to say that this one, okay. Now this is, let's just say this is y, okay, and r is also in this direction, okay. Now this one is say r, okay, and then this is dr, okay. Okay, let's just it is the y direction, but okay. Now if I had to say, all right, and then also let me also do this first. This r is the radial direction and this is r. So this is the maximum, this is the radius, r is the radius, of the pipe. Okay. Now what we just said, that there is a small layer which is near to the wall for a flat plate, actually, where there is laminar flow, right. So in that case, in this case, of course, what that is going to be is here, right. So there's going to be, right, let's just say we'll just call this as y. Okay. So when I say y, right, so in the sense that when I'm going to use this sort of a profile, right, so my y is actually good. So this relationship, this 1/7 law, is going to be valid only in this. So I have to subtract this height. I haven't written anything there. Okay. So let's just call that as y. Okay, let's just call that as y. So that in here, in this picture here, this is basically delta minus y, is where the 1/7 law is valid, because this is the turbulent part. This is a turbulent boundary layer with a laminar sublayer where the 1/7 law is not valid, right. So we have to do that. So similarly here, right. So we have this sub layer, the laminar sublayer, right. Let's just call this as y. Okay. So let's just say this one is okay. Okay, let's just say this is r, right? Then this bit, okay, this is y. Let that be y, okay, and this is actually r. Okay, so my y actually will start from here. Right, so my y will actually start from here. Right? Make sense? Right? So that my 1/7 law is actually here. So u is equal to u infinity y by delta to the power 1/7, and yeah, so this is valid here. So this is the laminar subrange, right. This is valid here as well as here. Yeah, okay. Then, so now we just basically have to do the math. Okay, let's do the math then. So also we, in this case, as you can see that the boundary is extending to the center, we can say that, right? Okay. So then let us sort of now start sort of do the math. Okay, let's see if we can do the math here. Okay. So in this case, what is delta? As you can see, this is the boundary layer thickness, right? So this is your delta, right, which is obviously equal to r. Okay. All right. Then yeah, so what is the velocity through this dr? Okay, so if I were to draw that also, for example, so say dr, okay, this is this region, okay, where the velocity is actually can be given by, this is u, this is the velocity, and which can be given by the 1/7 law, right. Okay, so this is your dr. Let us therefore write this. So in that case, now we are going to integrate this, like you must have done this before. Okay. All right, so let's then volume flow rate through the ring is equal to 2 pi r dr into u. Yeah, a simple math, right? And then we will integrate this, right? This is through the ring, and now through the pipe we just integrate it over y, isn't it? So then therefore volume flow rate through pipe Q is U R dr, right. So essentially where this r goes from y to capital R. So this r actually goes from say y to capital R. Make sense? Yeah, r goes from capital R. Okay. So we can do that, essentially this, or I can just simply, integrate this, because this we can do because we have, this formula available. Anyway, let us see. Okay. So we do that. Now, as you can see here, yeah, so r is equal to r, okay, plus y is equal to r, right. So therefore r is equal to r minus y, right. R is equal to r minus y, and dr is equal to minus dy. That's easy to see. That's just derivatives. Okay. Then, right, also delta is equal to r we have written here, right. Delta is equal to r, and the 1/7 law is also given here. Let's go ahead and input that into the Q, right. So then Q, okay, is 2 pi. Okay, I'm going to just not use the limits for now. Okay, then U is essentially U infinity. Okay, now this delta is equal to R. Okay, okay, let's first do this. All right, fine. So U infinity delta to the power minus 1/7 y to the power 1/7. So this is your U, right. Then you have R, which is r minus y, and dr, which is minus dy. Okay. Now this delta, right here, delta is equal to r. right, delta becomes equal to r. So, this is actually r to the power minus 1 by 7. Okay. So, then q is equal to 2 pi u infinity r to the power minus 1 by 7 integral r minus y, y to the power 1 by 7 dy, and this we put a negative sign. Okay. Let us go to the next page and write that out. We are just doing the math here now. See, or q is equal to minus 2 pi u infinity r to the power integral of, you see here, r into y to the power 1 by 7, right, and minus y to the power 8 by 7. Okay. So, it is r y to the power 1 by 7 minus y to the power 8 by 7 dy. Okay. So, let us integrate that and let us see what we get. So, this is equal to minus 2 pi u infinity r to the power 1 by 7, right, r into y to the power 8 by 7 by 8 by 7, because this is the power plus 1, right, minus y to the power 15 by 7 by 15 by 7. Okay. Right. So, this is equal to minus 2 pi u infinity r to the power minus 1 by 7, right, into 7, okay, by r y to the power 8 by 7 by 8 minus y to the power 15 by 7 by 15, okay, or q is equal to minus 14 pi u infinity r to the power minus 1 by 7 into r y to the power 8 by 7 by 8 minus y to the power 15 by 7 by 15. Okay. So, now since the maximum y is equal to r, therefore, at y is equal to r, what do we have? Q is equal to minus 14, this u infinity r to the power minus 1 by 7 r to the power, so because this becomes r 15 by 7, right, this becomes 15 by 7 by 8 minus r to the power 15 by 7 by 15. Okay. Then this is again equal to, we take basically the 15 out. Okay. So, this is so you see what we are doing. So, minus 1 by 7 plus 15 by 7, which is 14 by 7, which is 2. So, this is r square, right, 1 by 8 minus 1 by 15, right. So, you can see what is going on here now, 14 pi, it is easy now. Okay. So, this is 7 by 8 into 15. Okay. So, this is equal to 2/7 2/4, right, or Q is equal to minus 49 pi r square 60 u infinity. Okay. So, this is the total flux, right, and then mean velocity is equal to Q by this, right. If you see this, so which is equal to so by pi r square, that goes on minus 49 by 60 u infinity, right. This is what I think was asked of us. Right. So, this is what was asked of us, that what if the mean velocity is such, right, then yeah. So, I mean, this was our the question was that the velocity in a pipe with fully developed turbulent flow is a fraction of the maximum velocity, is Newton 1/7 law, which is what we did here, right. So, we are able to show that. It seems it's the mean velocity is minus 49 by 60 into u infinity, right. Interesting, right. So, here essentially what we have done is, for the value of to get a relationship between, or to get a velocity profile in the turbulent boundary layer. So, we use this. I don't think we really have talked about this earlier, right. So, we draw the velocity profiles. The velocity profiles look like these, right, what I have drawn here for a laminar boundary layer, but how does it look for a turbulent boundary layer? And this is where Prandtl gives us some idea, and he says that within a certain, beyond a certain laminar subrange in the boundary layer, when in a fully turbulent flow, there is an inner laminar subrange. So, and in the turbulent zone, minus the laminar subrange, velocity is actually a function of, velocity is a function of the free stream, is a fraction of the free stream, and also is a function of y, okay, which is related in this fashion, which is essentially the 1/7 law, right. Okay, so that is essentially some a particular example that I wanted to talk about. Okay, now let us look at one more. Okay, let us look at one more sort of a problem like this and see what we make of it. See what we understand. Okay, all right. Let's go to the next page. Okay, let me first write down. Okay, so now given the mean free stream velocity of a turbulent flow over a, so I think the idea is that one uses laws, right, which like the 1/7 law, as well as when we try to calculate the mean velocity, we use basic definitions, right, from first principles. So much of fluid is, this is the volume rate of fluid which is exiting the pipe, right, and you divide that by the area, and that gives you the mean velocity, right. So it's that is basic understanding, that is the basic fluid mechanics, and then we use specific laws which is pertaining to, say, the turbulent flow that we are concerned about now. Okay. So given the mean free stream velocity of a turbulent flow over flat plate, so the idea is that we have learnt a lot of concepts. We've looked at equations, right? We've looked at the difficulties in implementing those equations numerically using computers to solve them. So we've looked at all of those things, right? Having said that, given those concepts and my basic understanding of math and fluid mechanics, how do I implement those? So if I have been given a pipe, right, and I know that there is fully turbulent flow there, right, how do I calculate the mean velocity that will come out of there, right? How do I do that? So that was the problem which we just did. So in here again, the mean velocity profile is given, right, in terms of y of over a flat plate. Now let us see what is being asked from us. So y is the cross stream distance from flat plate. Yeah, we know that, right? I'll write it. Y is the cross stream distance from the flat plate. Okay. Let's take a friction Re, which is usually denoted as this, of 1000. Okay. So the friction Reynolds number is 10 to the power 3. Okay. Now draw the velocity profile for resulting turbulent boundary layer, right, and explain and indicate in detail, right, various aspects of the resulting velocity profile in the turbulent boundary layer. Okay, so I think we can do that. Okay. Explain and indicate in detail various aspects of the resulting velocity profile in the turbulent boundary layer. Okay. So let us see what are we talking about here, right. So what is this Re tau? I think if you remember, right, we said that there is a certain sublayer, right, a certain small layer within a boundary layer, right, within a boundary layer, where basically viscosity is most predominant, right, and we define individual scales for it, which is independent of the boundary layer thickness and the free stream velocity. So we come up with velocity scale, Reynolds number, length scales, and so pretty much that. So that these are specific to that range, right. So which is primarily guided by viscous forces, right. So Reynolds number, so friction Reynolds number is the Reynolds number in that length scale, right. So Now, we have been given this, the free stream mean velocity is given. So, what can we do with that? Now, shear stress near the wall, right? How do we do that? Shear stress near the wall. Now, we know this from earlier, the shear stress near the wall is entirely a viscous contribution, right, because it is a turbulent flow, right. We have been given a mean velocity, which is fine, but we do not have any idea about the turbulent quantities, which is the u dash and the v dash, right. However, at the wall, right, the shear stress is dominated by the viscous force primarily. So, we can write that at the wall, right, yeah, so we basically say at the wall shear stress is entirely a viscous contribution. Meaning, these quantities, or we had a term like this, right. So, anything with related to this can be ignored, right. So, these things do not play much of a role. So, the shear stress is entirely a viscous contribution. So, let us just say these things do not need to be taken into account. So, if viscous is entire contribution, then we can write tau wall to be equal to at the wall is 0. Is that right? Now, for in our case, right, u mean is given to us, and I can calculate the du mean dy. Can I not? So, let us do that. Du mean duy is 100 plus 24y y squared. Okay, and at y is equal to 0 is equal to 100. Okay. Therefore, tau at the wall is equal to 100 rho nu. Yeah. So, it is 100 rho nu. Okay. Then, let us do a few calculations. Let us sort of do a few calculations, because now we are talking about a viscous sublayer, right. So, let us just say the friction velocity, right. The friction velocity is equal to this, right. So, now tau w is essentially 100 g nu. So, this is equal to this is equal to 100 nu, right, which is, or u tau is equal to 10 under root nu. Okay. Then, so we let us calculate these scales, and then we can discuss. Okay. So, friction velocity, then we have a viscous length scale. right? Then we have a viscous, delta V is equal to nu by u tau, right? So, which is equal to nu, u tau is 10 under root this, which is equal to under root nu by 10. So, or delta V is equal to under root nu by 10. Okay, then friction Re tau is equal to, well, this could be like a cross check here. Okay, we could do that. We could do that. Okay, let's do that first. So it is delta u tau by this, right? But we don't know what delta is, right? So that's where, so now this is also equal to delta by delta V, if you see, right? So right here we've calculated delta V, right here. So R tau is that, and R tau is given to us, right? And this, or let's just say R tau is 10 to the power, what is R tau given to us as 10 to the power 3, it's 1000. Okay. Right, is equal to delta by delta V. Okay, so then delta is equal to (100) nu. Okay. We can obviously, you know, we'll put in a number for nu, and we should be able to get, you know, for air. So this is air, so we can figure out what specific value for nu is, and then we can, you know, get specific values. But I wanted to write this in this fashion so that we get an idea of, you know, because this is a viscosity that it is viscous dominated. So I wanted to just sort of, you know, give us a little more idea, or explicitly, you know, just tell us that how these length scales are varying. You know, the velocity length scale, the bundle thickness, right? Right. So we sort of do that, right? And while I'm going to write out this value, and why don't you take, you know, get specific values of that, and we'll come back in the next class and sort of discuss this one more time, and yeah, you know, then close it. Okay. So nu actually, so for nu for air, right, at 15 degrees centigrade is equal to 1.48 into 10 to the power minus 5 meters square per second, right. So given this, right, given this, I will leave you so that you can sort of work on finding out the values of u tau, delta V, and delta, right. And right, and then we will sort of discuss this and what this means in terms of the boundary layer, because that's the question, right, that's the question. So we'll draw the velocity profile, resulting turbulent boundary layer, explain and indicate in detail various aspects of the resulting velocity profile in the turbulent boundary layer. So I will stop here, and we'll take this up and complete this in the next class. Okay. Thank you.